Okay, so good evening, everybody. We will resume our session. So, if you happen to see the journey of learning this, did go through various aspects where we did try to talk about what is machine learning, how exactly we cater machine learning. We went into the technology part of it, the programming part of it, the stats part of it. Then we tried analyzing, understanding various data to see how you can do the exploration against it. And then we also went through the visualization aspect of it. And finally we also are trying to see what are all the various gaps which we identify at the different stages to see how they can be filled, right? So basically when we had the data very structured, way more unstructured, the problems which we have to deal with are completely different set. So that you'll have to understand the root level noding of things is very important, which means you should know what is that your data looks like, what is that you are trying to approach and achieve. Then it becomes immensely easy to select the various approaches from the available things and get going. So if you see this particular thing, we started our discussion yesterday on convolutional neural networks, where we try to define few things, where we say that when we have a fully connected layer, what are all the challenge? Because in a neural network, every neuron is connected to the preceding neuron completely. So that way the whole neural network becomes a computational heavy activity. And we saw when it is just a 28 pixel, not megapixel, 28 pixel photo, we get a 4-digit number. 28 into 28 into 3 layers, we get a 4-digit number. But the same thing when it becomes a 200 mega, not even megapixel, 200 pixel, 200 into 200, which is the 2 layers, and being a colored image 3 layers, we say 200 into 200 into 3, the number is a 5-digit number, more than 1 lakh. That are the number of weights what you have to put, which makes the whole process very computational heavy. To overcome that particular thing, we did try to borrow one of the things which was available as part of human eye, and that's where we said we will see if we can make a simple connection rather than a fully connected thing. And that's where we came ahead and saw the convolutional neural network based on the inspiration of our visual cortex. So we said visual cortex is a region in the brain where we try to get, or the stimulus gets fired based on certain sections. So basically we are trying to replicate the same in our programming approach using the various layers. So we have a convolutional layer, a ReLU layer, a pooling layer, and a fully connected layer. So we saw this being a representation of the alphabet X at a pixel level, and how we translate that saying it is X, R, O. And we also saw in an ideal case scenario, an X or O might not be in the same format what we saw in the first box here, right? The X or O can be distorted or can be represented in various ways. And we also saw the human eye being a 576 megapixel based thing, it can visualize the things much clearer than what we are making an application realize it. So with this being the backdrop, in this cases where it becomes little trickier, let's try to see and compare how exactly the convolutional neural network really works. Like the name says, it is a neural network. Definitely, there are neurons, the neurons are connected, but the approach is not ANN, it is CNN. ANN is the artificial neural network. Here it is convolutional neural network. So let's try to understand what we get to see here. So this is the ideal case X, the ideal case O. Now we have an image which we have to say whether this is X or this is O. What we try to do is this. What we do here is, and computer understands the image using the numbers at each of the pixel, which means we will try to put a number to every pixel in that image. In our example, we have considered the black pixel will have the value 1 and the white pixel will have -1. Easy representation. So wherever you have the pixels which are black, I have filled it with ones. So this horizontal line, sorry, this diagonal line and this diagonal line have values 1. All other boxes where the values are not at all available, I have refilled or entered the values -1. Now let's try to do the same thing with the image what we need to compare, which means this is an ideal image. This is an image which we have got for comparison. Here also I have done -1 or +1 based on whether the boxes are black or white. So here this is a black, therefore 1, this is white -1, which we get something like this, right? This is the 1 or -1 value. So my intent here was for all the boxes which are black, which have a value, I have put it as 1. Wherever there are no values or the boxes are white, I have put it -1. Now, if I try to union both of them and see, this is how my values look like, which means there are some placeholders which are common wherever I have put 1, which means those pointers also have the data in your reference and the new data set. Wherever I have put it in the red color X mark, you have either the data in your original or you have the data in your comparison. That's what the union of things happens. Now, see what we try to do this. What we do here, the CNN compares the image piece by piece. Every piece it compares, and the pieces that it looks for are called features, which means the smallest entity of an image, which is the pixel, it tries to see every piece of it. By finding the rough feature matches, it roughly the same position of the two images. CNN gets lot better at seeing similarity than whole image matching schemes. Now, if you see what we have done, the center box, it maps. The boxes on the side, it maps to see what are similar, what are not similar. So comparison is happening at the every box level. Now let's see what it does. Basically, we say every piece, what we do is called as a feature. So we go and try to compare the feature. Now this is my first box. Here diagonally I have 1 1 1. On the either side of diagonal line I have -1. Let's go here and see. Therefore, if you see, you have 1 1 1 diagonally, the center one, 1, 1, 1 diagonally, either side you have minus 1, minus 1, minus 1, minus 1. Now, if you see this particular thing, this is 1, this is the second one, this is the center part. This particular thing, whatever I mark, if I show you, let me mark so that we are talking the same. Now, if I see this, it is 1, minus 1, 1. If I go back, it is 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1. So the same thing is here also. Therefore, this is that center thing. This is the left hand top here, and this is the right hand bottom. Now, I did this 3 cross 3 matrix comparison. Once I do this particular thing, what I try to do is, if you try to see, I try to put it in the same image. Now, these are the small pieces of the bigger image. We choose a feature and we put on the image so that if it matches, then the image is classified correctly. Now, what I have, the red box here represents the red box. The blue outline box represents the blue outline box. The green outline box represents the green outline box. If you see 1, minus 1, minus 1. So 1, minus 1, minus 1. So this is this way. This is this way. In this case, only this way. Therefore, this becomes this way. Now, this is this way. Now, I have it only here and here. Which means you happen to see how exactly the mapping of the boxes became the features. Once you see this particular thing, this is one box, second box, third box, then what we try to do is we try to get it through the convolutional layer. What happens here? Let's understand that particular thing. Here, we move the feature, what we are talking, we say individual boxes and individual features. We move the feature or the filter to every possible position on the image, which means if you happen to see there are so many positions, we try to move that to that possible position. So if you see, the step 1 is line up the feature and the image, and second one, multiply each image pixel by corresponding feature image. Okay, so multiply each image pixel by corresponding feature pixel. So that is your step 1 and step 2. Let's see how exactly we do. Now we get this blue color box. So all of you just see it. It's very, very interesting. And your eyes today, when it is seeing and you are comparing with others, is also doing this without we explicitly knowing. So we are mimicking it. Let's see that interesting aspect. Now this is the blue color box. Now I have 1, and here also 1 into 1 becomes 1. Therefore, I multiply the corresponding pixel value. Therefore, I get my 1. Now, if I do the second thing, here in this box, I have minus 1, and here also minus 1. Minus 1 into minus 1 becomes plus 1. Therefore, I get plus 1. Third one, I continue doing it for all the 9 things, which means my recursive algorithm does that calculation for me. If you go ahead and if you see here, we move the feature or the filter to every possible position on the image. Then once we multiplied, we add them up and divide by total number of pixels in the future. See how we do. Step 1, we line up. Step 2, we multiply. Step 3, we add up. And then we finally go and see how exactly we divide the total number of pixels in that feature. Now, if you see this particular thing, I have the blue box. All right. If I see the blue box, now I have this values and I have this values. The values what I got after multiplying is this. Every pixel I multiplied 1 into 1 minus 1 into minus 1. We know, seeing the pattern itself, we know it is same. Therefore, all the boxes come as 1. Therefore, if I add all of them, I get 9. There are 9 boxes, 3 into 3, right? Matrix. Now you know how exactly the matrix will help. This is a 3 cross 3, 3 row, 3 column. Now the addition of that becomes the numerator 9. There are 9 values, therefore denominator 9. 9 divided by 9 becomes 1, which means the entire box gets the value 1. Once I do this, I put the value of 1 at the center. Now, to keep the track of whether that feature was, we create a map and put the value of the filter at that place. So, we put a value 1 at that place. Once you do this particular thing, we go ahead, move the cursor or the position to the next box. Now, see the interesting fact here. Here it is 1, 1, 1. In this case, minus 1. This is minus 1. Here it is minus 1. Wherever are difference, you see that. Now, this is what is the original. This is what we have got from this. Now, if you see, I get the values like this. I did not get all ones like what I got previously. Now, I get 1, 1, minus 1 in this 3 cross 3 matrix. Therefore, the sum of all of this divided by 9 gives me 0.55. It did not give me 1 like previously. It gave me 0.55. Now, I repeat this approach and go ahead, put into the center 0.55. After we do this, I go ahead, try to reposition everything, and I get a convolution layer output, which means for entire my matrix, I get the values. So if you see my 1 cross 1 or 0 cross 0, this is the 0th row, 0th column, right? Based on the index value, it is 0.77 minus 11 pi plus 11. Here we did this cell, we did this cell, so the same values. This is 1 and this is 0.55. I try to do this calculation for all the values or all the pixels available in the whole diagram. Once I do this particular thing, I get the output like this particular thing for my 3 patterns. For every other filter. So I try to compare that with all the 3 filters. Therefore, for the first filter, this is the thing. For the second filter, this is the thing. For the third filter, this is the value. So if you see, if you happen to do it manually, probably to do this particular matrix itself, you would require at least 2 to 3 hours to put these values. Right? If you see what is the matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cross 9. right? Imagine for you to do all this 3 times, right? This is the first time, second time, third time. That entire calculation has to be done by the system repeatedly, regressively. Okay, so we perform the same convolution with every other filter. Once we do, we get to the next layer, which is the ReLU layer. Okay, so what is a ReLU layer? You know what is a ReLU function, which means this layer we remove every negative values from the filtered images and replace it with 0. So if you see, it is either positive or 0 is the whole function of ReLU. It does not carry any negative values. Therefore, if you see, it is either 0 or positive. That is what is the functionality of ReLU. This is done to avoid the values from summing up to 0. So ReLU by definition is rectified linear unit. Rectified linear unit. Basically, it is a transform function, only activates if the node, if the input is above certain quantity, while if the input is below 0, the output is 0. Therefore, when we input rises above a threshold, it has a linear relationship with the dependent variable. So a ReLU layer works on that perspective. So if you see some examples, if my x is -3, function of my x will become 0 because this is a negative number. So my function of x is 0. While if it is -5, it still becomes 0. If it is positive 3, it becomes 3. If it is positive 5, it becomes positive 5. That is where the ReLU function really makes a difference. Now, with this, let's see what we do from each of the output from our filter. Which means we had our filters, there were some positive, there were some negative. So all negative values get converted to 0, all positive values are retained positive. Now 0.77, which was your first value, retains, second value becomes 0. We do it for the entire matrix of 9 by 9. Now post ReLU, post ReLU, this is what the matrix I get. I have all positive values or 0 values, no negative values. I do this on all the 3 features. If you see, this is my original thing, this is my ReLU, this is my post ReLU. If you see, there are no negative values in that particular thing. So we first did the convolutional layer where we compared every value, did the addition of the numerator divided by the total number of features. We did it for all the 3 features. We got the things. Then we applied the ReLU function where for every value which is greater than 0, we retained. Every value which is negative or below 0, we made it to 0. Now I have my ReLU function ready. Once I have the ReLU function ready or the second layer also done, I go to the pooling layer. What is a pooling layer? Very, very interesting, right? A pooling layer, we shrink the image stack into a smaller size. What we do, we pick a window size usually of 2 or 3. We pick a window size usually of 2 or 3, and we pick a stride usually 2 and walk your window across your filtered images. For each window, take the maximum value. So if you see, let's perform the pooling with a window size of 2 and stride 2. So we are taking that. Let me show this. What we do, this is a 2 cross 2 window. Now what I am saying, in our first window 2 cross 2, leftmost top corner, okay, the highest value is 1, so we track that and move the window to 2 strides. So therefore we see whatever is the highest we got. So we dimensionally reduce the whole thing into a smaller thing. We made a 9 cross 9 into a 4 cross 4, and we took this particular thing and we generated the value 1. Now now okay, I will see this. I will again repeat the ReLU. I will again repeat the convolutional. I know this is little complex, so just follow me. I will again repeat. I will have it for your questions also. Now what I am doing here is basically 0.7710 and 1. The highest of this I got 1. I will go ahead, do the same thing for my next box. In this box, the highest was 0.33. In this box, the highest was 0.55. In this box, the highest was 0.33. That way, I reduce this, the whole dimensionality. This is the pooling. So I converted a 9 cross 9 matrix into a 4 cross 4 matrix doing this. It became 1.3, 0.5, 0.3. Anyway, it are all positive values. We get it. Now, what I do, I get this for all the 3 strides. Therefore, I had my 9 cross 9, 9 cross 9, 9 cross 9. It is 4 cross 4, 4 cross 4, 4 cross 4 after the pooling layer. Now, in the interest, let me go back to the convolutional layer. I will repeat again everything. Just follow so that you are in the same wavelength what we are talking. If anybody has missed, also we will see. Now, if you see, okay, we came here trying to compare whether this x and this x are same. That was our problem statement. So we go here, we get the pattern for our first, where we said we will replace all black boxes with 1, all white boxes with -1. Then I did the same thing for both the boxes. On union, I get this particular thing. Once I did the union, I try to divide this into small and I'm trying to check if the features are same. In this case, I got the 3 features. The center one is the center, the leftmost, rightmost. So we take the 3 features as shown below. For these 3 features, what I got is we are trying to see the blue ones, the top left hand top, right hand bottom are the blue ones, right hand top, left hand bottom are the green ones, the center one is the red. That are the 3 filters what we had. For these 3 filters, I am going and applying my first layer. I said in CNN we have 4 layers: convolutional layer, ReLU layer, pooling layer, and your last layer. So the 4 layers of this, the first layer was a convolutional layer. So what we did in the convolutional layer, what we do, basically here we will move the feature or the filter to every possible position on the image. Now we line up the feature and the image and multiply each image pixel by the corresponding feature pixel. So what we did, we tried to get the first feature. We got our values. So if I see, I have 1 here, I have 1 here. Therefore 1 into 1 I multiplied, it became 1. -1 Here also I have -1. This is the yellow color one. This is from the blue color one. Now I get the -1 into -1 becomes 1. I try to do this for all the 9 pixels, which gives me a value like this. Therefore, after doing multiplication, I will do the addition of all the values of the pixel and divide by total values in the pixel, which is where I try to do this. Now I get this. Basically, I sum up all the values, then I divide the values by my total number of values in the pixel, which is 9 by 9. In this case, it becomes 1. This I repeat it for all the 5 or all the values I have identified, which becomes like this. From the first box, I got 1 at here. I do the same thing, creating a map and to put the value of the filter. So I have to do this for the entire 9 cross 9 matrix. Once I do that particular thing, I end up the values like this. Sliding the filter to the image, I get it like this. 1 in the center, 0.5. Then I do entirely, you see this particular box coming up, which means in this case, for every value in this box, here, here, you get the values which are filtered now. After comparing both, now once you do this, you have 3 features like that. So you have to do the same thing for all the 3 filters or features, which will result in a box like this. This is 1, 2, and 3. Once we get this particular thing, we have just completed the convolutional layer. Then comes our ReLU layer. What happens in the ReLU layer? It is all about retaining positive values or zero values, no negative values. So from my individual layer, I try to opt out all negative values by replacing it with 0. Therefore, in this case, I have positive, positive, this is a negative, it becomes 0. Again positive, which is 0.11 only, 0.33 only. This is the next one which becomes 0. Therefore, if I go here, I try to do this, and if I see all my values which are negative gets substituted by zeros. This is how I get my values in my ReLU layer. So this was negative, this was negative, this became 0, this became 0. Somebody was asking, how did we get the first line? Is this the one you were asking? I think, let me see, who was it? Navya, you asked about how do we calculate the first 2 rows. Was it here? Okay. Okay. Now here again you have -1, which became 0, minus 0.11, again this became 0. All the positive values which are positive, they are retained as positive. So I will put positive values as positive values. Whichever are non-positive values, those are the ones which got negated into 0 or substituted into 0. This way, I have to do it for all the 3 things. Therefore, this was my convolutional, after the convolutional calculation, this is after my ReLU layer, this is after my convolutional layer, which means this will not have any negative values. It will either have zeros or positive values. Once I have this positive values, I go to the third layer, which is called as the pooling layer. What I do in the pooling layer, I try to pick a window, usually of size 2 or 3, and stride off to usually what we do. The higher we take, faster the calculation is the accuracy. Lower we take, faster the slower the higher the calculation, higher the accuracy, right? So that's how it works. So based on the image, we might do the stride setting for your pooling. So let's take an example where we take the size 2 and stride 2. Therefore the 9 cross 9 I am trying to fit it into 4 cross 4 matrix. Now what I do, I take 2 cross 2. I said that I take a stride of 2 cross 2, right? Therefore I take a matrix of 2 cross 2. On my extreme left top, I have these 4 values. So in this 4 values, whichever is the highest value, I will replace that. Therefore 0.7701 became the value. Now if I go in my second case, 0.33 is the highest. So if you see this is my circle, 0.11, 0.33, 0.33 in this entire circle, which is 0.33, which is the highest. Therefore I take 0.33. If you take this circle, 0.33, 0.55, 0.11, 0.0, 0.55 is the 0. Then if you take this particular thing, 0.33 becomes your next highest. Therefore I reduced the whole 9 cross 9 into a 4 cross 4. This I repeat for all three my filters, which comes like this, where I have my stride input and get to see the output. This got my values which are created. Once I have done this particular thing, if I see, I have to do stacking up of layers. That was the last activity in my CNN. Now what I do, this is my original picture. I pass it through convolution, ReLU and pooling. Post pooling, the 4 cross 4 matrix values I have like this. Okay, I have like this. Once I have like this, I will go ahead and see what is available. Now, if you see, I continue doing that, right? Basically convolution, ReLU, pooling, convolution, ReLU, pooling. So what was a 4 cross 4, I reduce it to a 2 cross 2, which means I did again the same. You see, I did the convolutional, where I go through every matrix, get the values. After convolutional, I do the ReLU, where I knock out all negative values, retain positive values, then do the dimensionality reduction, retain the highest. I did this, which means this is iteration 1, this is iteration 2. This is the first iteration, second iteration. So a 9 cross 9 predominantly gave down to a 2 cross 2. Now it gets the fully connected class now, where okay, okay, now if you see this particular thing, then you go ahead and get your calculation completely at that layer. Okay, now what we do after this, let's see how it works in the fully connected approach. So this is your final layer, where the actual classification happens, whether whatever we shrinked, does it fit or not fit. So this is the value from my first, second, third. Let me put this, I am converting it into my ravel. Okay, so 1.5, 0.51, 1.5, 0.5, 0.5, 0.5, 1, 1.5. Now I got all these values got converted into rows. Now it is a single list. This I go ahead, I have a value for my original x and my original o, and when we feed in x and o, there will be some element in the vector that will be high, and consider the image what we see. So for x, these are the values. If you do the same thing for your o, this will what you get it. This, when we get, we go ahead and we consider the below input for the input image and below input for the compared image, and we will check whether it is the same image or not the same image. So if you see in this case, we get this was the original x and this was the original o. So if you take the new input, when we do all these three things on the new input, convolutional, ReLU, pooling, all of this, imagine we get the values like this. Here we have the values like this 1.5.5. If you just can remember, here you have 0.9, 0.65, 0.45, 0.87, you get the values. Now, when you go ahead, we try to compare it with the list of X and O and see how does this fare. The sum with the input X, if it is 4.56 with first one, 5 with the second one, we say 4.56 by 5 is 0.91, therefore it goes more with X. That way, if you do for the O, this is what we get, it goes with O. Therefore, here if you see in X, it is 0.91, with O, it is 0.51. Therefore, it is classified that as this goes more like an X rather than a O. Now, if you see the whole calculation for a simple 9 cross 9, I'm saying 9 pixel by 9 pixel, how it will do. Imagine you have thousands of pixels like this. Even if you take a 1 MB photo and see the size of it using your OpenCV, the shape, you see how big it is. And this, you have to first train, feed in the new image and help you to classify whether it is the same thing or not the same thing. That way, doing this is computationally lot more calculation intensive. So to do that whole thing and get the value, finally the algorithm will be able to classify the new input feed. Is it X or not X? Right? In this case, it says it is more inclined, therefore it gets classified as X and not as O. The whole working of this particular thing, let's try to see how we can go ahead and put a working model of this entire learning into a Python code. So basically we have this approach, we get the data set, we function to encode, then we have to resize the image because 50 by 50 itself is too big. I saw 9 by 9 itself calculated so much. I will reduce it to 50 by 50 and read it as a grayscale, and then I split the data 24,000 images for training, 500 images for testing. Once I do, I reshape the data using TensorFlow, build a model, calculate the loss, and use the optimizer with a learning rate as 0.001. Then I do the train and with the deep neural network for 10 epochs and then try to do a prediction. So if you see, let's see a use case where we have a dog and a cat classifier. Now let me go ahead, show you some data what I have. If you see, I have some data like this. Okay, there are like this is a 500 MB of data where I have some cats and dogs. It's a combination of cats and dogs, which I have large set of photos. If you see, this is my this itself is taking a lot of time, around 500 600 MB of data for cat and dog. I have now I have put this into the training where I said 24,500 images I will use for my training. And similarly, if I want, I will go for testing. I will use my another 500 images. So every time I pass this, it will say whether it is a cat or a dog. Okay. So as a human being, seeing this, you are able to. Now, if I have to do this through a programmatical approach, let me see how it will be done. So if I go here, probably this will take a significantly good amount of time. But what I have done is I have the code here. It was running for a long time. I don't know. This usually takes half an hour to 45 minutes for me to run. I did try to put, so still I don't know. It has not got completed. Probably we can put it on a collab and check that. So if you see this, this is the simple code for doing the cat and dog prediction. Now, let's see what happens in this program. Here, when we were talking about the test data, we said we have 500. When we were talking about the training data, we said we have 24,000 images. So if you see this, there are 24,000 images in this folder, which itself is of a lot of things. Which means I am trying to go and train my neural network, create a model based on this 24,000 images. Then I will have to feed in my 500 images and I will go ahead and test how does that look really. So that is the whole intent of this. And if you see this code, basically like any other Python code, I have imported the libraries what I need. So basically the NumPy, the operating system, the random, the TQDM library, TensorFlow, Matplotlib, TFLearn, all of this, whichever are required for me, I have done that. Then I give my path where I have the training directory, testing directory. So let's do one thing. Let's quickly take okay. So it's time. What we will do is let's take a quick bio break, come back, and then we will start seeing this in detail. That way we get the whole pulse of how exactly the program works. Okay. Okay, so all of you are back. Okay, so let's go ahead and see this working. Okay, now if we see this particular thing there, what I have, this program is like this. Now I first go import all the libraries, then I have my training parameter and the testing parameter, or rather the test data, training data, images. Then I say the image size is equal to what is that, and I give my model name dog versus cats. That is my model name what I create. Then I define a label where I create the encoding, because all the names which are there cannot be read, which has the we have to encode it with the integer. Therefore I give the label as cat or dog based on individual things. Then I define my one other function, which is the training data and testing data, where I loop through my entire data set in the training. So go to the path, convert that into the image, grayscale, convert the size into 50 into 50, and I shuffle the training data set and save it into one of the name, which is train data in npy, and similarly test data npy. This is the two data sets which I go ahead and create and save it. Now, one second, I think. Okay, probably if we put this, I give the right path. Okay, let me take the path. I have the training, and similarly I do it for the testing data also. I create the model which has both the values. After I do this particular thing, I go here and I get my values. So if I have already the data, I am good. Otherwise, I will go ahead and whatever I got created, I am doing this. Now this comes the whole aspect. So after doing the reshaping everything, I have these values. Now here is my model building for CNN, where we spoke about the various layers. So I have defined my convert, and I have the various layers, the ReLU layer, the convolutional layer, pooling layer, all of this I have defined. So if you see this, this is the data set, this is the pool where I have defined. And once I do this, I come to the last layer, which is my fully connected layer, where I give the activation type as a ReLU, and I go ahead and convert it. Once I do this, as I said, I will be using the Adam optimizer to reduce my loss, and then I use the TensorFlow, one of the function DNN, to convert that into the details of what it comes. So basically, once I do this, I do the model fit, like how we did it in the machine learning. We do the model fit. After I do this particular thing, I go here and check how exactly this, when I put the data into a cat or a dog, how exactly this particular things will run into place. So that is what happens. And if you happen to see that particular thing, this usually takes almost, because my laptop has a limited resources, if I use a GPU and put it on any of the cloud thing, it will run in less than 15-20 minutes. But since my laptop has a CPU, not a GPU powered laptop, this will usually take an hour and a half or two to run all the 24,000 images, do that entire calculation. And if you happen to see, the output will be something like this. Now what it will see is, I just took the when I ran the last time I did take this particular thing. If you see, it gives me the various observations, and if you see, the accuracy in determination at that point of time was around 88%. Now if you happen to see, this has classified it as a cat, though we know it is a dog, which is not a right classification. While this is a cat and it has rightly classified as a cat. While this is a dog, classified as a dog. This as a dog as classified as a dog. This as a cat classified as a cat. Don't take this below ones. Sorry, this has been taken as a cat, so this is also wrong. This is wrong, this is wrong, this is right, this is right, this is right, this is also a dog, this is a cat, what it has classified, which is wrong, and this is a cat, which means there has been, from a trained data set, when it really picked up the values, it gave you the details and it was able to ascertain certain things and classify which is a dog, which is not a dog, or which is a cat. So if you see, this is running and I have put 10 epochs, so therefore it still keeps running. All of this has to keep running. So probably if you see this, there are so many iterations which are going, all the calculations which we showed or which we went through it, the program is doing it for us. And if you see, it is ever increasing. Probably if we try to see at the end of the session, probably it could have got completed, is what I am seeing it. Now okay, so this basically gave us the insight into how a convolutional neural network works. So like we defined in a nutshell, it is an approach to classify, or rather understand the image at the pixel level and try to classify what is what. Therefore it is very heavy calculation, and the iterative process makes the whole process time consuming. Okay, so with this, let's get into one other thing of doing things, which is recurrent neural network. So RNN, which is your one other approach of doing things. Give me a second. Okay. Okay, so all this while we did two already available approaches from a deep learning standpoint, right? So they gave us some background in terms of what we do, how we do when it is a simple neural network, which is our ANN. When it is more to do with our images, it was more CNN. And now if you have to deal with one other unstructured data, which is text, right? We have one other approach, which we call as recurrent neural network. So this is again a deep learning approach where we use TensorFlow, Keras, all of them to do the things. So if you happen to see, like we discussed the other day, the deep learning algorithms are relatively used whenever you have your unstructured or semi-structured data. Therefore, let's try to see to address our approach for our semi-structured or unstructured data, which is our text, right? It could be handwriting detection or available of the current things, and we try to ascertain values. We will see the need for this particular thing. So the first and foremost, we saw the feed forward network, right? In ANN, we saw the feed forward network, but we will also now see what are all the limitations of the feed forward network. So what happens in our feed forward network? Let's get to see. Now, if you see, our trained feed forward network can be exposed to any random collection of photos, and the first photo it exposed will not necessarily alter how it classifies the second, right? So if you see this, seeing a photo of the dog will not lead the net to pursue an elephant next, which is very obvious, because if you see, at the output, you are not relating anything to your previous imagined output, right? So everything new is relatively considered as neutral. So when you have such challenges, you have to go ahead and see the feed forward network limitation. So for example, when you read the book, you understand it based on the understanding of the previous words. Yes or no? The sentence is very collaborative, cohesive, and it is related to what you need to get. So if you happen to see, when you are reading a newspaper, and in the newspaper there is a sentence which is talking about something to do with a cycle. Now you say cycling is very effective for your health. You definitely know what kind of cycle he is referring. You just does not consider a cycle to be a cycle brand product, right? It could be a cycle agarbatti, right? It is a product which is very different in category, but it is also called as a cycle. You know contextually which cycle he is referring, which means you understand based on the previous words what they have used. But you cannot predict the next word in the sentence if you use the feed forward nets. Ever give a try? Go ahead and try and see if you can predict without seeing. See, your eyes is the input source. Very difficult to do that. So if you have a neutral sentence written by somebody and your brain might be saying some prediction, the next word might be this, but if you actually see, the word might be very different. In sense, to predict the next word, it is very challenging, and if you use the feed forward network, you will not be able to predict things, right? With such a gap in feed forward, you have to see how exactly you can counter it. Basically, how can we address this challenge is a question which can help us to see what is there. right? Very, very, very challenging. See, basically, if you see, the machine learning is all about trying to have multiple solutions for various kinds of problems. Now, if I say a very, very simple example, it is like this. If 100 patients visit a doctor and 100 patients say that they have a fever, probably a doctor cannot come out of his clinic and say, all of you take a paracetamol and go. That does not work. One solution does not fit all the problems. Even though paracetamol is a solution for fever, each and every patient might have a problem differently. And that is what we get to see in your machine learning and deep learning. That way, what you get to see is how exactly you make the things very, very relevant, and how exactly you try to address them. Now, coming back to this challenge, how to overcome this challenge, let's see this particular thing. Now, how do we do this? It's very interesting. You have various inputs. Input at t, input at t minus 1, input at t plus 1. So, if I happen to take this, let me take this pen. So, this is at t minus 1, the word behind it, at the word, and t plus 1. Now you have to combine all of this to get your output. That is the way where we try to devise this recurrent neural network, or more practically it is called as RNN. Just out of curiosity, we will also go to see our Python code, how much it has run, to see if it has done anything significantly. Okay, so it has been running, it has been running. Okay, so we will allow it to run. Okay, so if you see this particular thing, let's say, what is our recurrent neural network mapped of? Now, if you go here and see this particular thing, see what happens. Now, a recurrent network, or type of artificial neural network designed to recognize patterns in sequences of data such as text, genomes, handwriting, spoken word, numerical time series from sensors, stock markets, and government agencies. Now, see this particular thing. A very interesting analogy I will try to make. Suppose your gym trainer has made a schedule for you and the exercises are repeated after the third day. That is what he has told you. He has taught you some exercises at a gym and he has said repeat it after the third day. Now let's see how this analogy actually works. Now see this. The first day he says the shoulder exercise, second day he says the bicep exercises, third day he gives you a cardio. Now if you see, based on day of the week, month of the year, or health status, can you predict the type of exercise? Day of the week, it could be any three: shoulder, biceps, or cardio. Month of the year, anything. Health status, anything, which means in the feed forward it is completely connected, right? So you have the problem of fix in this scenario, where if you try to do in the day of the week, you possibly end up doing things which are very, very irrelevant. So it could be you were asked to do a shoulder exercise, you might end up doing bicep. You were asked to do a bicep, you might end up doing a bicep, or vice versa. That permutation combination can keep existing. Once you happen to see this, if you see, this is what we have to get. Shoulder yesterday, basically you have to do bicep the next day. Bicep yesterday, you have to do cardio. Cardio yesterday, you have to do the shoulder, which means you have a dedicated link than one linking everything. So let me repeat it. If you see here, day of the week, month of the year, health status, which gets interconnected with all of these particular things, is your feed forward approach. Same thing when you see this, shoulder yesterday, bicep yesterday, cardio yesterday. If you do this, you get to do the whole thing in a sequence. So if yesterday it was shoulder, today it is bicep. If yesterday was biceps, today it is cardio. If yesterday was cardio, you do your shoulder exercise. That is the way you predict the type of exercise, which means predicted shoulder yesterday, which gives you a real map to bicep exercise. Predicted biceps yesterday, which means it goes to your cardio. Predicted cardio yesterday goes to the shoulder. And they keep interchanging. So if you happen to do such approach, you are reducing the stress on the network. At the same time, the predictability of the action what comes becomes very, very relevant. That is what the intent of your recurrent neural networks. So here the main intent of recurrent neural network is to see how exactly you map the input to the output without making it a feed forward or a fully connected approach. So this in summary is your recurrent neural network. So what we will do is we will stop here. We will take recurrent neural network in detail, get to the whole lot of things in tomorrow's session, but with reference to your convolutional neural network or any other topics. If you have any questions, feel free to put it on the chat. We will discuss on that point and then get going. Okay. So any questions, anybody with with regard to convolutional neural network or your any other topics which we have been talking? Go ahead. Okay, so what we will do is, I don't see any questions, but go through this things. If at all you have any questions, we can have the questions addressed and take it from there. And as I said, the link for all these documents will be shared by Dilip. The content for last 2 days I will share it with him today, and you will be able to see this content also by tomorrow. So, but all the previous content is already uploaded, and you will be able to go ahead and consume the content. Okay, so that way it helps you to address the things. Okay, so I think we are good. We will close the session and we will catch up tomorrow. Thank you.